Hello, my name is Jaden Cobb Samson with the matrix number 82614. To start off, we're going to look at the mechanical analysis. So for this part, we're going to look at the main components and the analysis part. So for the main components, there are going to be four main components, which are the stackable baskets, the railing system, handlebar, and the drainage system. And for the analysis, we're going to look at the parts that are considered critical to our design. So with the consideration of the safety factor of two, the L-shaped bar, which is part of the frame. Most of these is going to be part of the frame. The L-shaped bar has a max stress of 112.348 megapascal. The plate under the load sensor has a max stress of 104.64 megapascal, and the plate under on top of the load sensor has a max stress of 112.12 megapascal. And on the right, you can see our full design of our proposed idea.
My name is Sitanana Lincoln and I'm holding the matrix number of 82550, and I will briefly explain the material analysis of the buckle design. Referring to the drawing, component number 9, which is the top plate, is made from stainless steel 316. This material was selected for its side strength and excellent corrosion resistance in marine environment, allowing it to safely support heavy operational loads. The L-angle steel indicated by component number 3 is manufactured from STM A36 steel. This material provides sufficient structural strength, good weldability, and cost efficiency. Overall, this material selection ensures the buckle structure is safe, durable, and economical for repeated use. This section presents the static simulation used to verify the structural safety of the buckle design. For the 5mm stainless steel 316 top plate, a 200 kg load was applied with fully fixed edges. The von Mises stress is 4.61 megapascal, displacement is 0.094 millimeters, the safety factor is about 2, and the equivalent strength is 2.18 times 10 to the power of negative 5, indicating elastic behavior. For the STM A36 L-angle steel, the maximum stress is 130.7 megapascal, displacement is 1.72 millimeters, the safety factor is 2, and the equivalent strength is 5.93 times 10 to the power of negative 4, confirming elastic deformation. Overall, the structure is safe for repeated operation.
Hello everyone, my name is Elvena Sanagam with metric number 82540. This slide summarizes the torque and power requirement for the buckle transportation system. The total payload considered in the analysis is 340 kg, which includes the load of C product and system weight. The system operates on two different surfaces, soft sand at the beach and tarmac inland. Our motor sizing is based on the sand condition because it presents the worst case scenario due to high rolling resistance and wheel sinkage. From the force and torque analysis, the required motor shaft torque on the sand is 4.9 Nm per motor, and the required power approximately 0.32 kW per motor after applying a safety factor of 2. The sensor subsystem consists of three main components. First, the load set is used to validate the weight and ensure it is within the safe operating range before movement begins. Second, three IR sensors arranged in white, black, white configuration provide accurate line tracking and navigation. Third, an ultrasonic sensor is used for obstacle detection to ensure operational safety. All sensor signals are processed by the microcontroller, which implements the decision-making logic and send commands to the DC drive motor. This closed-loop integration enables autonomous operation and self-control to transport C product to processing center.
Boleh? Okay. Bye, Ben.
My name is Evan Jamri with metric number 82552. For thermodynamic part, this enclosure contains the electric components which generated heat. Since these components operate within a confined volume, heat accumulation becomes a key design concern. To assess the effect of internal heat generation alone, the enclosure was modeled as a well-insulated system. The temperature rise caused purely by the generated heat, resulting in a worst-case temperature of 248 degrees Celsius. In reality, the enclosure is not perfectly insulated, and heat can be transferred to the surrounding through the aluminum walls via conduction and convection. The maximum temperature is 72.6 degrees Celsius, which exceeds the safe operating limit of the battery, as the battery poses the highest safety risks under overheating conditions. In reality, the enclosure is not perfectly insulated, and heat can be transferred to the surrounding. Therefore, the enclosure was redesigned as an open system by introducing ventilation hole at the front and rear. As the vehicle moves, air will flow through the ventilation opening, causing heat removal from the enclosure. Hence, the maximum temperature is 35.8 degrees Celsius, which fall within the safe operating range. Therefore, the enclosure was redesigned as an open system by introducing ventilation hole at the front and rear.
Hello, my name is Francesca Analiton with matrix number 82566. For this fluid analysis, we wanted to see if the passive ventilation alone can keep our product cool. From the CFD picture, most of the air inside is only a bit warmer than ambient, but there is a small hot area near the component. As you can see on the slide, the analytical results show stronger airflow and faster air exchange compared to the CFD. This is because the analytical model assumes smooth, uniform flow, while the CFD includes real effects like losses and recirculation inside the box. Even with these losses, the air is still refreshed several times per minute, so the total air flow is enough. The main problem here is the local flow distribution. Some regions see weak airflow and become hotspots. Not because the system lacks total airflow, but because the air does not reach those components efficiently.
Everyone, for MechArms company, we implemented a process layout production line. This strategy is essential because we are producing a low volume of card with a high degree of customization. By grouping similar equipment into functional departments, we gain the flexibility to adjust the production sequence for each unit. To physically support this layout, we utilize an L-shaped facility flow. This geometry is critical for handling the card of 200 kg load, providing wide and arm strap path that reduce internal congestion. By separating the unloading and loading bay, we ensure a logical progression from raw material to finished product. This setup maximizes workers' precision, ensuring that heavy structural work and sensitive mechatronic integration occur in their own optimized environment. The MechArms production process is an 8-stages workflow designed for durability. We move from precision cutting and high-strength welding into a specialized mechatronic and a critical 10 hours anti-corrosion curing cycle. With a total lead time of 2080 minutes, we deliver one complete unit every 3.4 days, achieving an annual capacity of 90 units. To support this, we utilize an integrated storage system using cantilever racking for heavy steel and drawer cabinet for sensitive electronic, all managed through a strict FIFO protocol to ensure maximum efficiency in our job shop environment.
To end it all off, we're going to look at the professional and ethics. So for the laws and regulations that were considered in our designs are as followed. OSHA 1994, Food Act 1983, and the regulations from Board of Engineering Malaysia, or in other words, BEN. So that implemented the SDGs in our project were SDG 8, SDG 12, and SDG 9. And on the right, you can see the some of our risk rating or some of the risks that might happen during the usage of the product by the fishermen.
Now let's move on to our economic analysis. First, we separated variable and fixed costs as shown in the table. Most of our costs come from variable items such as materials and labor. But even with that, the total annual cost at our target of 90 units still allow a selling price that is realistic for small stream operators, which is 6,700 ringgit per unit. At this production, the revenue is clearly higher than the total cost. So the system generates a healthy annual profit and estimated return of about 30% on the money spent each year. Our break-even point is slightly below our target output, which means the project can cover its costs with a small safety margin. Over a 5-year period with a 10% discount rate, both the net present value and the benefit cost ratio are positive. So our product adds economic value rather than just breaking even. Finally, by improving physical efficiency from about 68% to about 85%, we also use raw material more effectively, reducing waste and supporting lower variable costs as well as SDG 12 on responsible consumption. In conclusion, our design achieves our main goal, which is to reduce manual shrimp handling, uses material more efficiently, and can be sold at a realistic price while still giving attractive profit and positive long-term value. This shows our design is not only technically workable, but also economically and environmentally sustainable for the local shrimp operators. Thank you. In conclusion, our design achieves our main goal, which is to